Hello everyone and welcome back. Over the last few sessions, we have been building our toolkit. We started with the very fundamental characteristics of the open channel flows and the Froude number. We then derived the speed of the surface waves, which gave physical meaning to that Froude number. We then explored the powerful concept of specific energy and how it governs the flow transitions over bumps and through contractions. And finally, we mastered the Manning equation for uniform flow. So that was perfect, idealized state where gravity and friction were in perfect balance and the depth remains constant. So let's be very honest. How often in nature or engineering perfectly uniform? So a canal might have a slightly changing slope. The bottom material might change, altering the friction. So, in these real world situations, the depth is not constant. This brings us to the today's topic, which is the gradually varied flow, or abbreviated here as GVF. So, this is the study of how water depth changes slowly and smoothly along the length of a channel. It's the bridge actually between the simple uniform flow we can calculate and the complex, rapidly changing flows we will see in the next section. So let us dive in and see what happens when dy over d of x is not 0 but is still much less than 1. So we have the key understanding of GVF in a single powerful equation, which is represented over here as dy over d of x equals to SF minus S naught divided by 1 minus Froude number square. So this equation might look intimidating, but it's actually a beautiful synthesis of everything we have learned so far. So let us break it down piece by piece. Dy over d of x is what we have learned up till now, what we want to find. So the rate of the change of depth with distance along the channel is the water getting deeper or shallower as we go downstream. So it's the quantity of that. So another is the S naught, which is the bottom slope. It's actually the driving force, the component of the gravity pulling the water downhill. We know this from our channel geometry. The third one is the SF, which is a friction slope. This is the slope of the energy line representing the rate of the energy loss due to friction. For uniform flow, we know that the SF must be equal to S naught, but here they are different. Froude number square is the square of the Froude number. This brings in the flow regime whether the flow is subcritical or supercritical. Now, where does this equation come from? We have to walk through the derivation starting from the energy equation. So we take the total head as h is equal to v square over 2g plus y plus z and differentiate it with respect to the x. So we know that d capital H divided by d of x is equal to minus s of f, which implies that the energy line slopes downward due to friction. And we also know that dz over d of x is equal to minus s naught, which implies that the bottom slopes downward. After some calculus and using the continuity equation to relate the dv over d of x to dy over d of x, we end up with this elegant result. The key step is substituting in the Froude number, which simplifies the kinetic energy term beautifully. But this equation is the foundation of GVF, gradually varied flow analysis. It's uh, uh, it's the representation of the water surface profile, the shape of the water along the channel, and is how it is being controlled by a competition between the bottom slope, the friction slope, and the flow regime. Now, let us think about what this equation means physically. The numerator SF minus S naught is representing the imbalance between the friction and the gravity. So there are three scenarios over here. If SF is less than S naught, which means the friction is weaker than the gravity, the flow would be accelerating. But if the SF is greater than S naught, The friction is stronger than the gravity, and in this case, we have the decelerating flow. But when we have the perfect balance of SF and S naught, we have the uniform flow there. The numerator is 0, and thus we can get dy over d of x equals to 0. So the denominator 1 minus fr, 1 minus fr square, 1 minus Froude number square is where the magic of the Froude number comes in. Remember that Froude number square is always positive, and if the flow is subcritical, Froude number is less than 1, so 1 minus Froude number square, this particular subtraction is always greater than 0. So the denominator is positive. But when the flow is supercritical, which means that Froude number is very greater than 1, so this subtraction term 1 minus Froude number square would give us the negative value, less than 0. So the denominator is in this case would be negative. Now here is the crucial insight that the sign of the dy over d of x, whether the depth increases or decreases, depend on the product of the signs of the numerator and the denominator. So let us consider a simple example. Imagine a channel with a bottom slope. There is milder than that is milder than the friction slope required for the uniform flow. That means SF is greater than S naught, so the numerator would be positive. So if the flow is subcritical here, the denominator positive, then dy over d of x would be equal to positive. So the depth increases downstream. But if the flow is supercritical over here with the denominator negative, then we have dy over d of x term as negative in the final, which concludes that the depth decreases downstream. So the exact same imbalance in the forces produces opposite behaviors depending upon whether the flow is subcritical or supercritical. This is why we can't just rely on intuition. We need the math also. Now, this leads us to the classic classification of gradually varied flow profiles. We have to mention that there are many possible configurations and standard references like French in 1992 and Cho in 1959 that who provide detailed classifications. So the profiles are typically named based on two factors. Number one is the slope of the channel bottom relative to the critical slope, which is the slope that would produce critical depth for a given flow rate. And the second one is a zone in which the profile lies relative to the normal depth, which implies that the depth for the uniform flow and the critical depth. So without getting too deep into the weeds, let us look at the few classic examples. Mild slope, hereby represented on this slide as capital M. This is when the channel slope is gentle. So the normal depth, which is represented as y subscript n, is greater than the critical depth y subscript c. So the flow is subcritical at normal depth. We have two curves over here, M1 curve and M2 curves. So M1 curve, if we have a mild slope and we create a backwater effect, say by a dam downstream, the depth will be above the normal depth. The equation predicts a gradually increasing depths as we approach the dam, forming a backwater curve. But when we have a M2 curve, if the depth is between the normal depth and the critical depth, the profile might draw down towards the critical depth. Then we have the another type of the slope, which is a steep slope, hereby in this slide represented as S. So this is when the channel slope is steep. So the normal depth Yn is always less than the critical depth Yc, and the flow is supercritical at this normal depth. So we have the S1 curve over here, so which implies that if we have a steep slope, but downstream obstruction forces the depth to be above the critical depth, so we need a different profile. So we get a different profile. So these profiles are not just academic or theoretical exercises, they are essential for predicting how far upstream a dam will affect the water level and how a channel will transition from a steep mountain stream to a milder valley floor. So now you might be asking, why is this important? Why do engineers spend so much time analyzing the gradually varied flow profiles? So here are the few practical reasons. Uh, Number one is the floodplain mapping. When we build a bridge or a levee, we need to know how far upstream the water will be backed up. The M1 backwater curve is the primarily the tool for predicting the extent of flooding during the high flow events. The second one is the channel design. If we are designing a channel that changes its slope, say for a steep section to a mild section, and so we need to know where the transition between flow regimes will occur. Will a hydraulic jump form? If so, where it will be forming? So this is crucial for lining the channel to prevent erosion process. The third one is the water surface elevations. For navigation purpose, the irrigation intake design, or simply the property line determination, we need to know the exact water surface elevation at every point along the channel. So uniform flow gives us one number, but GVF, which is a gradually varied flow, gives us the entire profile. So we have mentioned that the complexity and uncertainty of the flow geometry, especially in the natural channels, often means that a refined analysis is not warranted. But for engineered channels, understanding GVF is very essential. Now, gradually varied flow is very well defined by the condition that dy over d of x is less than, very less than 1. So the changes are slow and smooth, and the pressure distribution remains essentially hydrostatic. The streamlines are nearly parallel, and our one-dimensional assumptions hold reasonably well. But what happens when the changes are not slow? What happens when the dy over d of x is on the order of 1 or even approaches infinity? So think back to our very specific energy diagram and the ramp example that we have covered in the previous section of this topic. So, what if we have had made the bump or so high that the flow had to go through critical depth and become superficial? That transition at the crest of the bump is a rapid change. Now, also think about a sluice gate where the water flows under the gate at a very high velocity with a very shallow depth. Immediately downstream, the flow might be supercritical, but further downstream, if the channel slope is mild, the flow needs to return to subcritical conditions. If can't do that gradually, it has to do it suddenly, violently, through a hydraulic jump. So this brings us to our next topic, which is about the rapidly varied flow. So, in this section, we will study the phenomena where the depth changes abruptly over a very short distance. We will analyze the hydraulic jump where supercritical flow crashes into subcritical flow, dissipating enormous amounts of energy. So, we will also look at weirs and gates, structures that causes the rapid changes in flow and are used to measure the flow rate. Gradually varied flow gives us the smooth continuous profiles, but rapidly varied flows would give us the discontinuities, the jumps, and the flow control structures. Together with they provide a complete picture of how water behaves in an open channel. So let us recap that what we have studied up till now. We introduced the gradually varied flow as the natural extension of the uniform flow, where the depth changes slowly across along the channel. We also derived the governing equation as dy over d of x equals to sf minus s naught divided by 1 minus Froude square, which shows how the computation between the friction and the gravity mediated by the Froude number controls the water surface profile. We also saw that the subcritical and supercritical flows respond oppositely to the same imbalance of the forces. And we also touched on the classification of profiles and their practical importance for floodplain mapping and channel designs. So this sets the stage perfectly for our next lecture, which is about the rapidly varying flow. Uh, when the changes are no longer slow and gradual, we enter the world of the rapidly varied flow. So we will be starting with the most important example, which is about the hydraulic jump in the next lecture. So get ready for some exciting fluid mechanics. See you next time. Thank you.